All right, last diagram. Diagram number 6, Mr. Abbott again. You're looking at the Earth clock, but you're looking at the side view or the equatorial view. If you look at half of a sphere, when you're looking at half of a sphere, you're only getting 180 degrees. So whenever you get an equatorial view like this, you're only going to be seeing 12 hours of time. You could have put on the other one 24 hours. Okay, polar view gives you 24 hours, equatorial view gives you 12 hours. The sun's rays are coming from the right, which means this half of the Earth is illuminated. It is still an equinox because when you shade in the terminator here, if I shade in this half of the Earth in darkness, okay, the terminator is perpendicular to the sun's rays, so the terminator always goes straight up and down, okay, but that's the terminator, okay, so the terminator goes straight up and down, and you can clearly see that point H is on the terminator. You've got to realize which direction the Earth is rotating. This is the North Pole at A, so I'm going to put the axis here, I'm going to put North Pole, and to help me picture this, the Earth is rotating from west to east. Now, we need to complete the data table below. Point C is exactly at the point where the vertical ray is hitting. So if you're where the sun is hitting directly, if you're completely rotated and facing the sun, point C is going to be at 12 p.m., which means point C is at noon, so our time is 12 p.m. Now, opposite that, when you're facing completely away from the sun's rays, completely 180 degrees on the opposite side, point G is going to be at 12 a.m., so point G is at midnight. Point H is on the terminator, point H is on the terminator, and you're rotating into the light, which means point H has to be at 6 a.m., because I know that it's sliding from west to east, and point H would be going into the light. So point H, I'm going to look at this, and I'm going to say that's an AM, not a PM there. Point H is at 6 a.m. Now, the only longitude they indicated was that point H that we have here is 0 degrees, so point H, I'm going to write PM, well, it's the prime meridian. Okay, PM might confuse you because I'm not talking about times, but 0 degrees longitude is the prime meridian. Alright, if I'm looking at the prime meridian traveling this way, this would be degrees east, and this way is going to be degrees west. So I will leave the rest of this diagram and the rest of the table for you. It says the longitude lines are 15 degrees apart, so this would be 15 degrees east, or one time zone. This would be 30 degrees east. Okay, if I move back, west is earlier, so time would be getting earlier this way, and this line would be 15 degrees west. That line would be 30 degrees west. I'm fairly confident that you should be able to complete and fill out the remainder of this. But every line is 15 degrees away, which means if they're 15 degrees apart, there's a 1 hour difference, and that 1 hour definitely, at least for our school, one of the mnemonics that we use is wheel. Okay, it's either west is earlier, or if you look at it as you go east, east will be later. Now, I hope you got some help, got some assistance, that you understand these models to represent the seasons. If you go back to the first page, it lists the reasons for the seasons. Definitely, you should know the tilt of the axis. Okay, the Earth's axis is tilted by 23.5 degrees. That's a prime reason for the seasons. The revolution of the Earth around the sun takes 365.25 days. So part of the seasons deals with the revolution. You also have parallelism of the axis. No matter where the Earth is in its orbit, the axis stays parallel to itself. The North Pole always is pointing towards the star Polaris. So that axis, the Earth's axis, remains parallel while it is revolving around the sun. Hopefully this cleared some stuff up for you. We will be going on and working on this more. These are incredibly important models. Thank you for taking the time to follow along, and I hope this helped. Good night.